Good afternoon. It is my pleasure to introduce enGenome at this year's European Society of Human Genetics Conference. enGenome is an incredibly innovative company focused on the identification of rare genetic disease through fast and accurate interpretation of germline variants. My name is Jeffrey Anderson, a foreign sales representative here at enGenome. Today's agenda will include a brief introduction and background of our company. In our first session, enGenome's Chief Technology Officer will provide an overview of eVai, our flagship variant interpretation software. To conclude, our Chief Science Officer will explain the exciting research enGenome is conducting in the field of Digenic Variant Interpretation. enGenome was founded in 2016 in the city of Pavia, Italy, 30 kilometers south of Milan. We are passionate about delivering the most accurate genomic interpretation required to diagnose and treat rare genetic disease. enGenome provides an interplay of hands-on experience and software technology for the analysis and interpretation of sequencing data in clinical and research settings. Our bioinformatics products and services aim at providing accurate omics-based reports to physicians, thus improving diagnosis and treatment processes for patients around the world. Our team is made up of Italy's top bioinformatics professionals, including two of our co-founders who will present to you today, enGenome's Chief Technology Officer, Dr. Ivan Limongelli, and our Chief Science Officer, Dr. Susanna Zucca. Our team includes bioinformaticians, biotechnologists, and biomedical engineers, all focused on the identification of rare disease through modern approaches of bioinformatics pipelines, artificial intelligence, and automated software solutions. enGenome is a market leader in variant interpretation with a specialty in secondary and tertiary analysis. Our secondary analysis portfolio includes germline and somatic pipelines for gene panels, whole exome sequencing, and whole genome sequencing. Our tertiary analysis product, eVai, evaluates single nucleotide variants, insertions, deletions, and copy number variants, providing a top solution for variant interpretation in diagnostic and research settings. Additional bioinformatics services by enGenome include analysis for various applications, such as RNA sequencing, small RNA sequencing, ribosome sequencing. We develop custom pipelines according to our clients' specific needs. Our capstone tertiary analysis product is eVai, the expert variant interpreter. eVai is a software as a service that goes far beyond standard annotation. eVai interprets variant calling format files and provides automatic classifications applying ACMG, AMP, and ClinGen guidelines for single nucleotide variants, insertions, deletions, and copy number variants. eVai also performs family analysis, phenotype matching, and is GDPR compliant for advanced cybersecurity. eVai also features a proprietary pathogenicity score, which enables our users the tools to accurately classify and identify variants of unknown significance. Our flagship eVai software has seen rapid success in the Italian market, and enGenome is quickly opening channels for implementation of our services in labs throughout Europe and around the world. In Italy, our users have analyzed over 25,000 samples from undiagnosed patients in clinical settings. At enGenome, we believe the future lies with the clinical interpretation of digenic variants. Today, Dr. Susanna Zucca is on hand to tell you more about enGenome's exciting research in this field. But first, and without further ado, it is my great honor to introduce enGenome's Chief Technology Officer, Dr. Ivan Limongelli. Please remember to submit your questions anytime during the course of the conference, and enjoy the session.
Hi everyone, thanks for joining us. I am Ivan Limongelli and I'm going to talk to you about our software eVai. eVai stands for Expert Variant Interpreter. This is our CE IVD software as a service platform for genomic variant interpretation. It can cover different applications such as rare diseases and cancer predisposition, and in general, all monogenic disorders. eVai, moreover, can be used in different scenarios big diagnostics to sequencing targets, sequencing platform, and can be used to interpret variants that have been called by a broad range of variant callers. The ultimate goal of eVai is to accurately support and accelerate the judgment of the genetic expert in establishing the clinical significance of genomic variants. In order to do so, eVai combines four main features. It automatically applies ACMG guidelines, it stratifies variants of unknown significance, it enriches the variant with inheritance pattern in case of family analysis, and last but not least, it allows to match variants to the phenotype of the patients. So we have automated both ACMG guidelines for single nucleotide variants and insertion deletions, and ClinGen guidelines for copy number variants. Both these guidelines suggest to independently evaluate many information about the variant by matching and extracting the available data from different resources. Focusing on ClinGen guidelines for copy number, all these evidence or criteria are grouped into 5 main sections regarding, for instance, genomic content, functional effect, matching of clinical literature, and inheritance patterns. Let's have a close look at one of these sections. This is just the first part of it. The complexity of this guideline application relies not only in checking the information suggested by the criterion itself, but also in the section and criterion interdependency, in the logical operation that may link more pieces of evidence, and finally, in the application of the scoring system used to assign the final classification. Now, eVai software is able to tackle all this complexity, and starting from a VCF file containing the variant of interest, it integrates dozens of resources from one side and digests the guidelines from the other, creating a genomic knowledge-based representation that is used to programmatically verify the guidelines evidence and generate the final score and classification. Moreover, it is important to note that in eVai, score and classification for a variant is predicted according to the known a priori possible related conditions. For example, let's consider this intergenic deletion of the PTN gene, involving more than one of its exons. Now, accordingly to the MET gene, PTEN has been associated with different genetic conditions. And applying the guidelines in the light of that, the classification of these deletions results more pathogenic for Coden syndrome rather than macrocephaly and autism syndrome. And this happens because eVai triggered one additional criterion, in particular 4B, by finding a similar copy number variant in ClinVar with the same genomic content associated to the same condition and confirmed de novo. So, guideline section 4 is about the evaluation of use cases found in published literature and other possible sources. In order to check these evidences, eVai uses 4 main datasets: ClinVar and Decipher for previously established classified variants, and DGV and NeoMed for comparison of the target variant with those found in the general population. Now, eVai computes CNV similarity based on different factors, such as the type of the copy number, the classification of the matched variant in literature, the reported associated condition, and the genomic content. So, for instance, this target deletion is involving 2 genomic features of interest, a gene and an enhancer. Now, eVai finds 3 overlapping pathogenic deletions in ClinVar or Decipher. However, because the genomic features involved by these 3 deletions are slightly different, eVai will select only those CNVs that have a more similar genomic content based on the pathogenic class. A similar approach, but stricter, is used to check common or benign duplications. Finally, to test the performances of eVai in the automatic CNV classification, we have conducted a benchmark analysis on expert-reviewed copy number variant using data from ClinGen web series and from the guidelines validation study. We have observed a high concordance, as you can see from this slide, between the expert manual curation and the eVai predicted class. even without using all the patient's phenotypic and family segregation data that were available to the experts. As a plus, we did not observe any confirmed pathogenic variants predicted by the software as benign or likely benign. And now it's time to see eVai in action. We will briefly explore its basic functionalities. We will look at examples of classified copy number variants, and I will show how the software allows to deal with the burden of sequencing artifacts. And here we are looking to analyze a sample with eVai that has been opened in our so-called variant browser. The variant browser is divided in two main sections. The one on the left is showing the list of the interpreted variants that have been found in the original VCF file. In this sample, there are almost 30,000 of variants. Each of these lines represents a variant, and each of them has been automatically classified accordingly to ACMG guidelines. You can see the classification and the number in brackets that represents the so-called pathogenicity score for a variant. Now, because in this case we are looking at single nucleotide variants and insertion deletion tabs only, we have applied our own score to weigh the ACMG criteria. This score is not influencing classification that follows ACMG guidelines rules, but it is highly correlated to it. You can expect pathogenic variants having a higher score rather than uncertain and benign ones. But more important, through the score, you can pinpoint those uncertain significance variants that have been associated to more pathogenic evidences than the others. For example, here we can distinguish 3 uncertain significance variants with a score of 4, followed by 2 variants with a score of 3.5, and so on and so forth. Going down the list, variants have less supporting evidences, and so may have more benign evidence associated to it. Each variant line has several information, such as the gene, the predicted effect, the HGDS nomenclature, and some icons working as a shortcuts. For example, this icon shows that the variant is an heterozygous, while this other variant over here showing that the variant is an homozygous state. Then we have this gray square that we call inheritance tag, that shows the possible inheritance patterns associated to the variant. In this case, eVai reports the variant as de novo. The inference of the inheritance pattern here is possible because the sample problem has been analyzed within a family, in particular with the healthy parents as a trio. Looking to this variant instead, the inheritance tag reports us that this variant is a recessive compound. And by mouse overing it, we can see the possible second hit. In this case, this is an uncertain significance variant with a very low pathogenicity score, so we may exclude it as possible second hit. Then we have finally this icon that reports the number of times the same variant has been found in all the samples analyzed with eVai by the specific user. The viral cycle also indicates that the variant has a matching ClinVar, and it reports the corresponding classification there. The second section of the variant browser represents a possible genetic condition that could be associated with the variant. As shown in the previous presentation, eVai is driven in the classification by the data available for the conditions that can be a priori associated to a gene or a genomic region. In the example here, we can see this variant has been associated to Schneider-Guidon syndrome, and for this condition, the variant is pathogenic with a pathogenicity score of 11. But also, this variant can be considered uncertain significance for mental retardation with a pathogenicity score of 5. Indeed, we have different criteria that have been triggered for the two conditions for the same variant. Variant can also be adjusted for classification in case we need to modify ACMG evidence. For example, adding new criteria. We can save the results, the adjustment that now is likely pathogenic, before was uncertain, and then we can confirm the variant disease association. So by confirming the variant, basically, we are submitting the variant to an internal user-specific knowledge base that allows the software to reuse this information for other variants and adjust ACMG criteria accordingly over time. Each variant can be explored in details by clicking on the corresponding variants row. We have different sections here that reports VCF extracted information such as variant coverage, the quality, the filtering, the variant allele frequency. Then we have other sections like the ClinVar section that show the matches and publication sections, or the lab findings that list the other samples having the same variant. These are links, so in case we can click on it and open the sample in another variant browser sample sheet. Now this open sample here reports also a tab with copy number variants. So when we click on it, we can see the list of classified copy numbers and the score accordingly computed according to ACMG guidelines. Each copy number comes with the main information as the involved gene, the CNV type, the variant size, the genomic content, and also some icons that are basically reporting the most similar matches of CNV in ClinVar or the Cypher databases. Also here, each CNV is linked to possible conditions. And we can see the ACMG ClinGen criteria, click on it, and look at the evidence that have been automatically evaluated by eVai in order to trigger the criterion. In this case, this variant had a similar deciphered pathogenic variant reported for the same condition under evaluation. Then by clicking on the copy number variant row, we can explore different details as well, such as the genes and involving exons, the most similar ClinVar and decipher copy number variants with direct links to these databases. And finally, a filter section on the left can be used to search among the list of prioritized variants. Filters are divided by categories, and in this case, by common and specific sections for single nucleotide variants and copy number variants. Common section include, for instance, the possibility to filter for gene list. We can type the name of the gene here, or copy and paste list of gene of interest and apply the filter. We can also load saved filter, saved the gene list. So for instance, I can load this one, comprehensive of 5 genes, and then I can apply the filter in order to be reused in different samples. Common section also include the possibility to match for phenotype. So basically, phenotypes terms can be searched in text-free form, and HPO terms can be used in combination to filter both single nucleotide variants and copy number variants. So each applied filter results in a list of prioritized variants according to their pathogenicity, but matched for the information of interest. Here we can see that for this condition, autism, on 9 possible phenotypes, we have 2 matches. And the same kind of matches are reported for single nucleotide variants and insertion and deletions, highlighting the most pathogenic variant associated to conditions with these phenotypes. Finally, I want to show you a functionality that we have recently introduced to deal with sequencing or variant calling artifacts that may be present among the top list of pathogenic variants. So let's suppose to look at this variant and we judge its quality, we check its quality, and we judge that maybe this is an artifact. Eventually, we can label this variant as an artifact and extend also the artifact to other samples, matching samples. But let's suppose to just label the artifact for this sample. So we have labeled this variant as an artifact, and we can choose to hide the artifact with this function over here. So now if we go to a sample having the same matched variants, we can see that an artifact nudge appear, and we can basically accept the nudge or deny the nudge or simply ignore it. But nevertheless, we can always hide possible artifact as well. So that's all for the demo part. Now I will leave the floor to my colleague Susanna Zucca. She will talk about our new exciting research software that goes beyond monogenic disorders. In case, however, you are interested in trying out the software, please visit our website engenome.com and request a demo over here. Thank you.
Hi everyone, I'm Susanna Zucca. In this section, we will present our new research tool, which will build upon our eVai software. Currently, genetic diagnosis is focused on the evaluation of each variant separately, with a monogenic approach. As geneticists well know, over 40% of patients who receive the modern genetic test by genome sequencing remain undiagnosed. And 1 out of 2 patients that have a genetic disease have an unclear diagnosis as well. We have decided to go beyond the one gene, one disease paradigm and develop a new technology that applies artificial intelligence to the identification of oligogenic variant combinations. The simplest case of oligogenic inheritance is digenicity. Therefore, we are excited to introduce our new algorithm that we believe addresses these issues. Presenting DIVAs, the first of its kind Digenic Variants Interpreter. Now, let's briefly introduce the concept of digenic inheritance. We have 3 different scenarios. In the first, referred to as true digenic class, the presence of variants in 2 independent genes is required to trigger the disease, while the presence of a single mutated gene does not cause the disease. The second class, named composite, covers a primary driver variant with modifiers. In this scenario, the individual carrying the primary variant can present symptoms of the disease, with the modifier variant impacting the severity of the symptoms or the age of onset. In the third class, we have dual molecular diagnosis, wherein 2 disease-causing primary variants in different genes lead to 2 independent clinical diagnoses. DIVAs can detect digenic variants belonging to all of these 3 classes. DIVAs is a machine learning-based algorithm trained with data from the DIDA database, the 1000 Genome Project dataset, an internal enGenome dataset, and published scientific literature. The input is patient information, including a complete list of mutations and phenotypic traits in forms of human phenotype ontology terms. DIVAs computes all of the possible digenic combinations with all the available variants and calculates a score used both for classification and prioritization. The output is a list of all possible digenic combinations, ranked according to the probability of causation. Preliminary findings are really intriguing. We reach 97% sensitivity and 98% specificity on test set. Today, DIVAs is patent pending. To validate DIVAs performance, we tested it on solved clinical cases, and I'll present you an extract of our results. The first clinical case, kindly provided by Professor Valente and her group from Mondino Foundation in Italy, is related to 2 male siblings with phenotypes involving cerebellar hypoplasia, microcephaly, seizures, behavioral disorder, peculiar face dimorphisms, and severe intellectual disability. Both siblings share a common hemizygous driver variant in the PAC3 gene, known to cause most of the phenotypes. However, to explain the extreme severity of ID and the peculiar dimorphisms, a second hemizygous modifier variant was found in the FRMPD4 gene, known to be associated with ID. This case of composite digenicity was analyzed by DIVAs. The algorithm computed more than 80,000 combinations of candidate genes harboring potentially causative variants and sorted them according to how fitting they are with the patient's phenotypic landscape. The digenic combination known to be causative, composed by variants of the PAC3 and the FRMPD4 gene, was classified pathogenic by DIVAs and ranked in the first position. As we can see from our eVai variant browser for one of these samples, these two genetic variants were classified as variant of unknown significance and have low pathogenicity when analyzed separately. With a monogenic approach, it's difficult to identify even with the addition of our DIVAs algorithm. These genetic variants are now identified, improving the outcome of diagnosis. The second clinical case is from Mondino Foundation and Spedali Civili Hospital in Brescia, Italy. Here, two fetuses from consanguineous parents were affected by Meckel-Gruber syndrome, that is a lethal ciliopathy. Both parents are heterozygous carriers of two mutations in two distinct MKS genes. The TMEM67 variant fully segregates with the disease within the two affected fetuses. A second mutation of the MKS1 gene, either in the homozygous state for the first fetus and in heterozygous state for the second fetus, correlates with phenotypic severity. DIVAs computed more than 60,000 combinations of candidate genes for both fetuses. The Digenic combination known to be causative was ranked in the first position for both. Here, it's worth noting that the associated scores were slightly different due to the different zygosity of the MSK1 mutation. A third clinical case was provided by Professor Carabba and a group from Cagranda Hospital in Milan. The patient here was diagnosed in adulthood for severe CVD with leaky phenotype, including lymphopenia, neutropenia, splenomegaly, and hepatomegaly. The patient has a pathogenic variant combination involving CARD11 and the STAT3 gene. The last variant was somatic, while the first one is under investigation to determine its somatic or germinal origin. In this case, DIVAs computed more than 50,000 gene combinations, evaluated them with respect to patient's phenotype, and created a ranked list. The non-causative variants were placed in the top 5 combinations. As you can see, DIVAs is a promising solution to identify Digenic variants combinations. If you have unsolved clinical cases or cases where a single mutation was found but not enough to explain phenotype severity, please contact us at info@engenome.com and visit our e-poster.
Well, thank you, Susanna, Dr. Zucca. We do appreciate that. So we are running out of time here, and we have received many questions during the course of the program. So we're going to try to just answer a few. And for those who will not have their questions answered, please do email them to us at info@engenome.com. So the first question that has come in here is for Ivan on the eVai platform. Ivan, is it possible to analyze quartets and duos rather than trios?
Okay, thank you, Jeff. Sure. Basically, during family analysis configuration, is it possible to configure relationships between family members and analyze also quartets composed of selected probands, unaffected or affected proband sibling, for instance? Or maybe you may also want to analyze just the mother and the father and the proband only. In that case, surely there is some criteria that are relaxed by eVai, so eVai will evaluate only some missing information and will share the inferred inheritance tags accordingly. So, but it is possible, yeah.
Okay, thank you very much. The next question we have is for Dr. Zucca about the DIVAs platform. Is DIVAs available as a software, and can they have a free trial?
Okay. Thank you, Jeff, for the question. Well, in this moment, DIVAs is an R&D project, and we surely aim at introducing it in eVai once its validation will be completed. At this stage, what we are doing is to collect genomic samples from researchers or clinical institutions, and we run DIVAs algorithm on them and give back prediction results. So for sure, if you are interested in testing DIVAs on your undiagnosed cases, you can contact us and send information to info@engenome.com.
Okay, great. And let's see, we've got another question here. And this question is for Ivan. Ivan, do you need a control reference for CNV analysis?
Well, control reference, basically, it's here we are talking more about happy number variant identification. So with eVai, we are more focused on clinical interpretation. So basically, clinical interpretation according to ACMG ClinGen guidelines. So for variant code identification, you should have the copy number variants formatted in the VCF file. Also, we basically keep the information from the VCF, so deletion duplication. Also, we deal with precise or imprecise copy number variants, but the copy number variants should be in the VCF file, should be stay there, and obviously in the right format. I mean, you can use different tools to call copy numbers. I can cite JTK, exon depth, Manta, Dragon, whatever. But some of these tools can use a control reference. Some other can use other kind of algorithm. We can provide also support in doing it, but this is out of the scope of DIVAs, more for the copy number variant identification part. Yeah.
Okay, thank you very much, Ivan. And we're out of time here, but we can answer one more question. So we're going to keep going. And I have my third question here for Dr. Zucca. And this is a specific question about DIVAs. And the question is this system peculiar for ciliopathies, or can it be used for different diseases?
DIVAs actually is a pan-disease method. And as for all machine learning-based tools, the strength of the tool is the availability of a representative training set with known digenic instances. And this is the key to get good predictions. And this is why we invested time and efforts to build a comprehensive digenic dataset. So basically, DIVAs is not focused only on a single class of diseases, but is pan-disease. And as an example, we also tested on psoriasis, as an example.
Okay, that's great. Well, everyone, it looks like we are out of time here. So I just want to speak for everyone in saying thank you for participating in our session today. And please feel free to reach out to us at info@engenome.com. And we'd be happy to answer your questions. And we'd really look forward to working with you. So thank you, and have a great European Society of Human Genetics conference. Thank you so much.
Thank you all.
Thank you all. Bye.